Hello guys, and welcome to a new chapter of physics, the photoelectric effect. The photoelectric effect is the third chapter of optics, after we have studied diffraction and interference. So, the importance of this chapter is that it reveals a new aspect of light. After studying light as an electromagnetic wave, whether in diffraction or interference, photoelectric effect is an experiment which cannot be explained using a wave. Throughout the chapter, we're going to talk about this in more details. Before we do that, I will just like to shed some light on the long debate which scientists had about the nature of light. So first, scientists used to think that light is a stream of particles. For example, Isaac Newton suggested that light is made up of particles having colors. Then Huygens came and suggested the idea of having waves. We have talked about this in diffraction. Thomas Young produced an experiment in which he confirmed that light is a wave in which we have superposition producing constructive and destructive interference. So, with no doubt, after the experiment done by Thomas Young, light was adopted to be, and as used to be, as a wave. Now, with the photoelectric effect, papers and cards were shuffled again. Scientists had to think again, what is the nature of light? Because explaining the photoelectric effect demanded new insights and new ideas about light. So the first experiment that was done by a German scientist called Heinrich Hertz. Heinrich Hertz, I think you know him for his family name because it's the Hertz, the unit of frequency. Now, before we indulge in the photoelectric effect as a study, let's check the main points that we're going to cover in this chapter. We're going to observe the photoelectric effect. We're going to define what a photon, I think you have heard about the term, and what its characteristics are. We're going to define threshold wavelength and frequency, and we'll go to work function and define it as well. You notice the majority of this chapter, of this part, not chapter, is about definitions. So it is going to be a bit boring, yes, because it doesn't have any new ideas, any new calculations. It's all about defining terms, define this and define that. First, I would like to look at these pictures here, not the German flag. The German flag has some insight, some idea for me. I'll keep it for you later to understand. So we have these three figures here, in which you have a calculator with a solar cell, solar cells covering a roof of a house, and solar cells in a satellite. Have you ever wondered about the functioning of solar cells? How do they capture sunlight and produce electricity? Again, at the end of the chapter, we will be able to answer these questions. Not at the end of this part, at the end of the chapter, which is after the second or the third part, depending on the durations that we take. So let's move on. The first idea, we're gonna go over the experiment done by Heinrich Hertz in order to study the photoelectric effect. First, I have a video here recorded for an experiment in which, you know what, let's take some ideas, some points, okay? I have here the text about it. We observe that, okay, we're gonna observe it after looking at the experiment. We have an electroscope. You all remember what electroscopes are from grade 10. It has a zinc plate here, and this plate and electroscope all together is charged negatively by some means, okay? Once it's charged negatively, the leaves move apart. Now we're gonna shine some light on the leaves and observe. Let's go to the experiment. Ultraviolet light here. It's sending light towards the zinc plate, which you can barely see here. Leaves were diverging and they start collapsing. After 2 minutes and 26 seconds, the leaves move back to where they are. Now, if I go a bit back here, and okay, pause it here, you notice that the leaves approach each other. So what happened here? As if the ultraviolet rays made electrons leave the plate so that this plate becomes uncharged. And when it becomes uncharged, the leaves will collapse. So what is the effect of the radiations there? Simply removing the electrons. This emission of electrons from a body, metal in general, after receiving radiant energy, which is light here, is called the photoelectric effect. So the first definition of the photoelectric effect. This experiment was studied by a lot of scientists since the year 1887 or something like that. Now, no one was able to explain this experiment because all people were trying to think about light being a wave, until another German scientist came, and his name is Max Planck. Max Planck in the year 1900, suggested that light isn't a wave. Light is a stream of some different type of particles. He called these particles photons. Now these particles, regardless of their name, have a very important characteristic. They carry a unit energy, and we'll refer to that later when we reach energy. Right now we're just defining terms. So a photon is a particle, an infinitesimal particle of light. So the first idea I mentioned here is light has a corpuscular nature. So keep in mind that in this experiment, light is a particle and not a wave. So this particle is called the photon. So we can think about it as one pebble, one unit of light, as if light is sending these particles here. We can count them, okay, even though the number is going to be extremely large. What are the characteristics of a photon? It has three main characteristics. A rest mass of 0, charge 0 as well, and its speed is the speed of light that we know. Now, until today, 2020, the whole characteristics and behavior of photons isn't completely revealed. There are a lot of things that we do not know about photons, and we are still studying them. However, for this chapter, it's enough to understand these three terms. So moving on now, we're gonna have like a quick quiz about questions. So first, indicate the aspect of light revealed in the diffraction of light experiment. Indicate the aspect of light revealed in the photoelectric effect. And third, a monochromatic radiation is made up of photons. Give two characteristics of a photon. Answers, think about them. So first, light diffraction. It reveals the wave nature or the undulatory aspect. Photoelectric effect is reveals the particle or corpuscular aspect of light. And what are two characteristics of a photon? I've chosen here 0 mass and 0 charge. You could have easily chosen, for example, it moves at the speed of light, c. You can, later on we're going to study energy, you can say that its energy is given by this. It is a particle carrying 1 unit of energy. Anything that we build up later can be used as an answer here. Okay? So now we'll move on to the experiment. So in this experiment here, you can see that we have a source of light with intensity which can be adjustable. If first is 0, so it's turned off. Now we can change the type of the light here. It's indicated in nanometers, thus it's the wavelength. We remember that V equals lambda f or C equals lambda f. When wavelength decreases, okay, the color will change and the frequency definitely increases. So this one here on the very far right side has the highest wavelength and the shortest frequency, and at the very end we have the shortest wavelength and the highest frequency. So moving from right to left we increase frequency, and moving from left to right we decrease frequency. Moving from right to left we decrease wavelength, the opposite or the inverse in fact. Moving from left to right we increase the wavelength, كمان the opposite or the inverse of frequency. Now I'll choose some intensity. First I have chosen sodium as a metal here. Let me explain about this a little bit. This device is called the cathode tube. We have a cathode plate here covered by a certain metal which we can choose here, connected to a battery and another plate which is the anode. As we shed light on this metal and electrons are ejected, if any, we need these electrons to move towards the anode. This is what we call the photoelectric effect, extraction of electrons. Now to confirm that electrons move from here and towards this plate directly, we can add a battery, but I want you to forget about the battery for the time being. We just need to notice and observe what happens when we shed light on the plate. With sodium, I'm gonna put the intensity in 10, nothing happens. 20, so I'm increasing the intensity gradually and nothing is happening. Why is that? Why do you think nothing happens? Intensity is very high. I expect that when light reaches here, it might heat this up, then electrons should move. However, nothing happens. What would happen if I change the frequency or the wavelength? As we decrease the wavelength here, color is changing, but nothing is happening. Something weird happened here. Electrons started being extracted. So we can observe the photoelectric effect. If I continue, photoelectric effect will keep on being observed. So going back to this remarkable point, if I move a bit before and or more as wavelength, nothing is happening. Some electrons are still being ejected. Less, again, some electrons are being ejected. With yellow light, no more electrons were ejected. So as if the color has something to do with it. Let's check what happens if I change the metal to zinc. The experiment was done with zinc. I try more colors. Nothing happens. Now the experiment that was done used ultraviolet. So let's go to ultraviolet. Excellent, electrons are extracted. So it seems that the type of the color is important to the electrons moving. Let's go to calcium. With ultraviolet radiations first, moving this to ultraviolet. Definitely it's going to happen. So as if ultraviolet radiations are capable of producing the effect always. Decreasing. Now I know the value that I'm searching for, that's why I moved quickly. If you don't, you move slowly to check which critical value like limits or sets a boundary between emission and non-emission. 419 almost, there are some electrons. 430, nothing happens. So it's something between 430 and 419. Let's go to 425. Electrons were emitted. So there is like a boundary between emission and no emission, somewhere between 425 and 430. Can I get 427? Let's check. 428 was good. 428 produces nothing. So this is weird. For any value from 428 and more as wavelength, nothing happens. Less emissions will start. So as if 428 or 427 is like a boundary between emitting or not emitting. Okay? As wavelength is less than this value, emission happens. More, nothing happens. Now we know that wavelength and frequency are inversely proportional, so I can deal with the same discussion but reversing my speech. For a frequency less than this value here, which corresponds to 428, nothing's gonna happen. For a frequency more than the frequency corresponding to 428, electrons will be emitted. I wonder what might happen if I increase the intensity now. Electrons are being emitted, I increase the intensity. You notice that the rate of electrons increases. Electrons extracted will be extracted at faster rate, at higher rate in fact. So this is a quick overview on the experiment. Now I would go back with you to the flip chart to answer some questions just to set ideas clear before we move on. First, what is meant by photoelectric effect? I need you to write a certain definition for photoelectric effect. You can check what we have done before, which is photoelectric effect is the emission of electrons using some convenient radiations of the surface of a certain metal. Second question, why do we call them convenient radiations? Well, to answer that, I will focus mainly on what we have done in the previous experiment when we used metal, calcium metal. For lambda being less than or equal to 427 nanometers, emission happens. Greater, nothing happens. So yes, the radiation should be convenient to produce the effect, because for some values, no effect will happen. Now this is a nice question. Can this phenomenon be explained using wave nature of light? No, I've answered this before. But my question is why? I would like you to think about a way to explain this using waves. Next time when we meet, we can discuss your answers. Now I'll move on to the second reflection of the experiment.